let's say that we have something that's in an unstable state that will undergo a decay process. For example, we might have an excited atomic state, an excited electron, that is going to drop back down to the ground state and release a photon. Or maybe we have a radioisotope that's undergoing a decay process. Okay, let's take a look at that. And let's say that the probability of a decay for this object is 10% sometime in the next 5 seconds. So what does that look like? Well, let's say that we've got some sort of rate of decay, and that's going to be equal to the probability that we were given divided by delta t. So we've got a probability of 10% sometime in the next 5 seconds. And so that gives us a rate of 0.02 1/seconds. That's effectively the probability of a decay in a second. If we were to go and put in 1 second here, we will get the probability of a decay in 1 second is 2%. We could take a look at that. Let's quickly note that. So if delta t is 1 second, then the probability here is going to be equal to r delta t. I'll make a note of that off to the side. And so that's going to be equal to our 0.02 1/seconds times 1 second, and that's equal to 0.02, where probability is equal to 2%. All right, what about as t goes up? Well, the longer we wait, the more the chances of this decay happening. So we could say, well, what about delta t is equal to 10 seconds? Well, then our probability is our rate, 0.02, times 10 seconds, which is equal to 0.20, or 20%. So a much higher likelihood that the decay will happen in that amount of time. We'll do one more. What about if we wait 30 seconds? Well, then the probability will be our rate times our time, and that's going to be 0.60, or 60%. So there's a 60% chance of this decay happening in 30 seconds. Now, the other obvious thing that we should consider is, well, what happens when we have a probability of 1? Let's take a look at that. Let's say 1 is equal to our r times delta t. And so that gives us a delta t that's equal to 1/r. And in this case, that's equal to 50 seconds. So we expect that this decay will definitely happen within 50 seconds. And this particular time is what we consider to be tau, or the lifetime. Okay. Now, that's for one individual. What if we have a large population of these atoms or radioisotopes? So what if we have a large population for example, of excited atoms or radioisotopes. Okay, well, then we have a slightly different but very closely related situation where we have the probability of any of these decaying is going to be equal to n times the probability of any individual. And this n is the number of excited atoms or whatever. Okay, and so we can also write that as saying, well, now this is n r delta t. So it'll depend on the rate, the decay rate, the amount of time, and how many there are. Now let's write that in terms of the change in that population. So our delta n is going to be equal to negative n r delta t. Now, why is it negative? So it's negative because it's a decay process. It's going down. The number of excited atoms, for example, you start with is going to be declining based on this rate and the amount of time and the amount you start with. Okay, so we have this in terms of the change, but let's take this. So let's take delta t to dt and delta n to dn. So we're going to look at an incremental, a really small incremental change so that we can look at our rate here. So now we have dn is equal to negative nr dt. So now we can express this as a rate of change. dn dt is equal to negative nr. And so this gives us this rate of change of the excited atom. Now what we really want is an expression for n at any t that would be very useful. So how do we get there from here? Well, the first thing we're going to do is take a look at our n and t values. So let's bring those to the same side. So we're going to go dn and bring the n value down, and then that will be equal to negative r dt. Now that we're in this form, I'm just going to bring this down. I'm going to copy this so that we have it for reference. Okay. So what we're going to do is now integrate both sides, and this will enable us to get an expression for n at any time. And that's going to be a very useful equation. So let's integrate both sides. So we'll integrate on the dn n side, and we're going to integrate from n naught, so the initial amount that we have in that population of excited atoms or whatever, and we're going to go to n, some later amount. And then we're going to go over this side. We don't need to include the negative r, that's just a number. and we're going to integrate dt. I'm going to integrate dt from 0 to t. Okay. Now, the integral of 1 over n is a pretty standard integral, and that's going to be equal to ln n, evaluated at n naught nn. And that's then going to be equal to negative r, and then the integral of dt is just t, evaluated at 0 and t. Okay, so let's substitute these values in. So then we have ln n minus ln n naught is equal to negative r, and we have t minus 0. Now remember your log rules. Ln n minus ln n naught is ln n over n naught. Remember, ln is just a log base e. Okay, and we have minus rt. We're getting close. Now, this is fine, but what we really want is an expression for n is equal to some set of values. So how do we get the n value out of that ln expression? Well, we're going to put both sides into the exponent of e. So we're going to say, well, let's go e to the ln n over n naught is equal to e to the negative rt. And when we do that, now we're able to eliminate that ln expression. And recall, this is a log identity. So ln x is equal to log ex. So we're really talking about, log identities here. And so since we have, really it's e to the log base e, then we can rewrite this as n over n naught is equal to e to the negative rt. And here we are. We can now rewrite this as n is equal to n naught, e is equal to, or e to the negative rt. And this can also be written as n is equal to n naught, e to the negative t over tau. And going from there to there, we recall that r is equal to 1 over tau, and that tau is the lifetime. Although it takes on a somewhat different meaning in the context of a larger population, and we'll see that in a moment. Okay, so let's take a look at what this means. I'm just going to give ourselves a little bit of room to stay on one page here. What does this expression look like? Well, it's an exponential decay. And what does that mean in terms of a physical system? So maybe we can't fit it all on one page, but I wanted to make sure that I went through it step by step. So maybe I will move this such that it's here. Okay. So let's take a look at what this is going to look like. So this is going to be an exponential decay. And so at t is equal to 0, for example, we have n is equal to n naught. If you look at those expressions, you have e to the t over tau. So if t is 0, then e to the 0 is 1. So n is equal to n naught. Now if t is equal to tau, what happens there? Well, we have n is equal to n naught, e to the negative 1. So that's going to be equal to 0.37. So that's 1 over e, and e is 2.71 times n naught. So what does that mean? So that means that after tau, seconds or whatever units, 37% of the original remain. And 63% have decayed. Now, if t is equal to 2 tau, then n is going to be equal to n naught e to the minus 2. And that means 0.37 squared n naught. And so that means n is equal to 0.14 n naught, and so 14% of the original remain. And 86% have decayed. And we'll just do one last one to really emphasize this point. If t is equal to 3 tau, then n is equal to n naught e to the negative 3, which is 0.37 cubed n naught. And that means that n is equal to 0.05 n naught. So that means that only 5% of the original remain. And 95% have decayed. So often in some cases, you'll see this as a reasonable threshold to say, okay, well, 95% have decayed, so 3 tau is an important threshold. And I've plotted this out as an example where we have exponential decay of some sample, and I chose to start the sample with 100 so that it's also going to match up with percentages. So let's just note a couple of things here. We can start out by noting that what's going to be our tau value? Well, it's 2 seconds. That's written on the plot. And so that means that tau is going to be here. So this is tau. And then this is going to be 2 tau at 4. And 3 tau. 3 tau at 6. And if we kind of look at where those values are ending up, so let's just zoom in here. So a tau, or 2 seconds, where is that? well, we're looking quite close to our expected value, so that's 37%. So that first tau amount of time has a huge decrease. That's the exponential decay. And then we can say, well, what about the next tau? So 2 tau. And that is going to be our 14%. And our final value that we were looking at just a moment ago, that's 3 tau. And that's our 5%. Now there's another value that may be of interest here that we haven't yet talked about, and that is the half-life. So after how much time has 50% of the original population either decayed or remained? So let's take a look at that. And let's take a look at that on the plot here. So I'm going to pick out 50% and then draw this down here. So this amount of time is a special amount of time. So this is 50%, and that's our half-life. And you can see here that the half-life is going to be a little less than tau. And then if we treat that half point here, this 50% point, if we go another one of these intervals, it's going to halve again. And we're going to get into that next. So here is our half-life. And so at every one of these time intervals, the amount that decays is going to halve the sample again. It's going to be half as much, half as much, half as much every time this amount of time passes. So let's take a look at that. And we'll work that out and an equation for that as well. So, after how much time is half left? And, of course, half has decayed. Well, let's start with our equation for the amount at any time. So n is equal to n naught e to the negative t over tau. Okay, let's find the time where we have half of n naught. That's going to be our half-life time. Okay, so that's 1/2 n naught substituting in for n. It's equal to n naught e, and this is a special time, so let's denote t 1/2 over tau. Okay, so immediately we know that we can cancel these n naughts. And so now we have 1/2 is equal to e negative t half over tau. And we want to solve this for the t 1/2. So to do that, we're going to take the ln of both sides. Okay. So if we do this, now we can bring down, because of our identities around logarithms, we can bring down this exponential. And so we have negative t1 half over tau ln e, but ln e is just 1. Now, here's where we can make a choice. This is fine. We can solve for t1 half right here. But I find it a little bit more elegant to change ln 1 half to negative ln 2 to eliminate that negative sign. Either is perfectly fine. And so now we can rearrange for t of 1 half, and we get tau ln 2. And that's our relationship between the half-life and the lifetime. It's this factor of ln 2. Another way to put this is the half-life is 0.69 tau. All right, there's another version of this equation that you will see, and it can be quite useful. It can be quicker for some types of problems. And I want to show you how to move from this to that. Okay, so what we can do is substitute in this relationship between t1 half and tau into our original equation for the number at any time. So we're going to sub it into this equation. And so then we have n is equal to n naught e, and so now we're going to substitute in for, now we're going to have negative t, but then for tau, well, tau is equal to, and maybe I'll note it down here, well, tau is equal to t 1 half over ln 2. So in this case, if we're substituting this in, we're going to have t 1 half ln 2. Okay, great. That doesn't look terribly convenient, but let's simplify this a little bit. So next we're going to look at, well, I'd like to get rid of the negative sign. So let's go n, and I'm going to go e, and we'll say, well, this is t ln 1 half over t 1 half. Okay, and you'll see why. I think that's helpful. All right, so now let's bring the n's together. So we've got n over n naught is equal to e, and we've really got t over t 1 half times ln 1 half. Okay, so when it's written in this way, what does this remind you of? If we zoom in just to this and consider what we have is an expression of t over t 1 half times ln 1 half. Our logarithm rules allow us to take this and move it up into an exponent. So that's what we're going to do. And at the same time, what we're going to do is introduce, so hold on here. So let me just rewrite this. So now we have n over n naught is equal to e to the ln 1/2 to the t over t 1/2. And I just want to kind of remind, so I was doing this color. So just remember log rules, that a log a x is equal to x, and e to the ln x is equal to x. So these identities are going to enable us to get to the useful equation. So what we have now is the ability to rewrite this e to the ln. Well, these are effectively canceling each other. So now we have n over n naught is equal to 1/2 to the t over t 1/2. And there we go. This is another useful equation where we are able to relate our n value. We could rewrite it in the same form as before. N is equal to n naught 1/2 t over the half-life. So now we have a version of this equation that is in terms of the half-life instead of tau. It's a lot of work to see where these equations come from. For the most part, you will use them as tools to solve different problems. But I wanted to show you step by step how they're all related and where they come from. That's all.